Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this video is an introduction to machine learning as part of the course Analytic Methods for Lawyers. It's the first in a fairly lengthy series of videos on this topic. The objective here is to expose you to a branch of mathematics, analysis, computer science that has absolutely exploded over the last decade or two. We've had incredible advances in computer vision, things like self-driving cars, medical diagnoses, analysis of text, synthesis of data, and many, many other fields. My purpose here is to give you an idea about some of the main areas of machine learning and to show how they're implemented in Wolfram Language. The first area I want to discuss is supervised learning. The idea here is you have some data, you have a right answer, that's the supervision, associated with that data, and what you want to do is to create a machine, and really it's just a piece of software in 99.9% of cases, not a physical machine, although it could be, which when confronted with similar data is likely to produce either the right answer or something close to the right answer. So actually, the various forms of regression we've seen, you could think of as a form of supervised machine learning. The idea there is they take a model architecture, which is the basis functions. That's what you're going to stick coefficients in front of. And after you run various computations that use the data, the training data, we produce a function that we hope will predict the right answer when confronted not only with the data already seen. We hope that it's unbiased enough, that it's flexible enough, that it can kind of accommodate the existing data that it was trained on, but also that it will do a good job predicting data that it's never seen before, the so-called test data. So the process by which you go from this supervised data to a piece of software is known as a supervised machine learning algorithm. And there are a huge, huge number of algorithms that have been developed over the years. Many of them have basically gone by the wayside because others have been found to be superior, but there are still a significant number of algorithms, and some are better suited for some tasks than others. So, just as there are distribution families or firms, as I've called them, that produce particular distributions, the factories like normal distribution 2, 3. Each of these algorithms, like a random forest, for example, will produce software that has certain elements or certain operations in common, but just as a normal distribution isn't specific enough to tell you how something's actually going to behave. Similarly, there are a zillion kinds of random forests, and that's true even if you're using the same algorithm every time to produce them. Plus, there are actually, all of these algorithms have little variations or sometimes significant variations attached to them, and so when you say someone's doing a random forest, you have a pretty good idea what they're doing, but you may need to look into the details. In any event, so like a decision tree will produce an architecture that will sort of sequentially separate data based on one of the features, and then take the two branches of data that might be produced as a result and run a decision tree on each of those branches, which will produce more branches, and then it'll run decision trees on each of those branches, and so you kind of recurse your way down until you're pretty sure what each of the pieces of data actually is. Or a random forest and gradient boosted trees actually produce lots of decision trees and a rule for how you combine their results. Or a neural network, you'll start with an architecture of layers. There are usually not an infinite number of layers. They're kind of like Lego pieces. There are maybe a large variety, but maybe not an infinite number. And you put them together and the data flows through the Lego pieces, except that the Lego pieces, the layers, have often have, not always, often have parameters in them that will be updated during the training process. Or in symbolic regression, I'm just going through a list of supervised learning algorithms here, certainly not all of them. In symbolic regression, you're going to basically think of mathematical expressions as trees, and you're going to split up the trees and recombine them or mutate the trees in a fashion that is kind of like evolution of chromosomes. And so what you end up with is a tree, or maybe a collection of trees, that represent ultimately mathematical expressions, basically formulas that you can then apply to data. Or in nearest neighbors, you get what's called a nearest function that basically tells you, hey, the nearest point on which we trained of your piece of data are the following 5 points, and maybe we then have a method by which those 5 points get to vote on what the outcome of your method, your point should be. And then there are machine learning algorithms that actually take the output from other machine learning algorithms and combine them. So you might take the output from an ensemble of machines, maybe a gradient boosted tree and a decision tree and a neural network, and feed that output into yet another kind of machine learning algorithm, maybe a support vector machine or something like that, and create output from that. This method of sort of taking the output from machine learning methods and feeding it into yet another machine learning method is called stacking. There's another kind of meta-algorithm in machine learning. It's called boosting. It's a form of supervised learning. And the idea is you take some not so good machine learning algorithms, maybe even an algorithm you've crippled in some way. It might work fast, but it might not be very accurate. You produce some function, some predictor function, just as we've discussed. Maybe it's a decision tree, maybe it's something else. And you apply the function to the data and you see how you did. Now, points that the function got wrong are then given higher weights. You know you need to pay more attention to getting those points right. You run the new algorithm again. And this time you hope that you get the former errors wrong without making new errors on the thing that you earlier got right. And you then basically weight the results of the two models that you've run, and then you reweight things that you've now gotten wrong. And you keep iterating through this process until, at the end of the day, it generally turns out you have a pretty good model that's made up of essentially weighted submodels. There are lots of nuances here, lots of variations, gradient boosting, eta boosting, all sorts of stuff, but that's the concept of boosting. Let's talk about the two major super functions that Wolfram Language uses to handle supervised machine learning. These are predict and classify. They're very similar, but predict is used when what you're trying to predict is something that's continuous, that could take on any value from -5 to 38 and anywhere in between. Classify is used when what you're trying to predict is discrete, like setosa, versicolor, or virginica, or spam, or not spam. The idea of these super functions, though, is that instead of being forced to figure out which machine learning algorithm works best, predict and classify do a lot of that work for you. They basically do some experiments very quickly to see which kind of algorithm seems to be doing a good job. Now, they have lots of options that let you override this, what's called AutoML or automated ML, and you can tell it how you want the supervision, the machine learning algorithm to be done. But you don't have to, and that's quite an advantage. Moreover, I would say in my experience, until you're really pretty good at machine learning, I would stick with the AutoML provided by Classify and Predict. It seldom makes a bad selection. Maybe sometimes you can get something marginally better, but usually not materially better. All right, let's take a problem and see how Predict actually operates. And I'm going to use that Boston Homes data that we saw in connection with statistics. The form of the training data is it's a list of rules. The left-hand side of each rule is data about the home, and the right-hand side is the price of the home. And I'm going to do my through terse dimensions thing so that we just see a snippet of the data and the length of the data. So here's what each data item looks like, and here's how many data items we have. Now, let's run it through Predict. This is the whole thing. This is it. Predict, and here's our data in the appropriate form. I'm going, watch carefully because it's going to be fast. All right, there we go. You could see it if you watch quickly, figuring out what method to use, and ultimately generating a predictor function, which I've assigned to pre. We can press this little plus button, get a little more information on the predictor function. It learns that it had 338 pieces of data to train on, and that ultimately it used boring old linear regression to do the job. Now, I actually would like to explore use of a different method, and so I'm going to rerun it and force it to use gradient boosted trees by using a method option. So there we go, and we're done. All right, let's see how this predictor function pre actually performs. So let's get the first 5 examples of the training data. This one here means I'm only picking the characteristics of the home, the features. I'm not including the price of the home. There's our first 5. Now, let's apply pre to all those 5 examples at once. Pre is smart enough, we don't have to use map. It's a function that's what's called listable, meaning it can just work on a bunch of lists at once. All right, and there is what the machine predicts the price of these homes are. So let's do that. Let's grab part 2 of Boston training. Here's what we're going to do. And we can see we did pretty well on number 1, pretty well on number 2, pretty well on number 3, not well on number 4, and pretty well on number 5. So our predictor seems to be retrofitting well to the data that it was trained on. It doesn't have so much bias that it can't accommodate most of the data, although the fact that it's getting this one pretty wrong is distressing. All right, let's now add a second argument to pre-distribution, and instead of getting the a point estimate of the value of these homes, we're going to get a distribution. That distribution will be centered on the point estimate, but we will have a standard deviation around it. And by the way, that's why that 20 to 27 thing is troubling, because it's like a lot of standard deviations away. In any event, let's see, though, how our predictor function performs on data that it's never seen before. That's usually what you're trying to do in machine learning, and probably what you should be trying to do in statistics as well, although that is not the traditional approach that statistics has taken yet. All right, we're going to get the test data, and I'm going to do my through terse dimensions thing, and there we go. All right, let's retrieve the first 5 homes, just for example, in the test set. Let's apply pre to, that's our predictor function, to that test data, and those are the values we get. Again, let's compare that to the actual values of those homes, Boston test, 1 to 5, item 2, and that is certainly not right. What have we done? All right, proving that your professor is susceptible to dumb mistakes. That should be a comma, not a semicolon. And now we see we got number 1 real great, number 2 meh, number 3 bad, number 4 pretty good, number 5 pretty good. So the good thing is that our predictor is generalizing fairly well to data that it's never seen before. All right, what else can we do? We can get pre is one of these objects, and where's our pre? There's our pre. It's one of these objects that has lots of information embedded inside it, and we might want to know, hey, what's inside you? And so we have this discovery mechanism where we say information, pre, properties, right? And we learn there are all sorts of properties that are embedded inside that pre object. So we might want to determine whether L1 regularization was used or L2 regularization was used. What are those? L1 regularization is basically lasso that we saw in the statistics segment of this course, and L2 regularization is essentially ridge or Tikhonov regression that we likewise saw in the first section of this course. Now, when we run this, turns out they weren't using lasso or ridge, but if they were, it would show up there. And by the way, when you run predict, you can actually insist that there be regularization by actually setting L1 and L2 regularization. We might want to find out something about the method that was used, and so there's a method description property, and it gives us a sentence roughly explaining what the gradient boosted tree algorithm is all about. Often what we really want to do is to see how our data is going to perform on data, how our predictor is going to perform on data it's never seen before. And the function that's going to do this and give us a lot of measurements of performance is predictor measurements. The arguments are the predictor that we built and the data that it's never seen before. So we're going to run that, and we get a predictor measurements object. And we can, for example, now see, hey, what's the R squared? This R squared, by the way, is the same R squared we saw when we did statistics, and it's 0.801773. We might want to see how does our the actual value of the home compare to what we predicted for the data it's never seen before. And by and large, it's doing quite well. There are some outliers here where we're saying we think this home is worth 28, and in fact it's worth 25, and we think it's actually worth 50. That's really bad. And this home we think is worth 44, and it's actually worth 22. And you know, if we wanted to improve our performance, we could say, well, these must clearly be outliers, let's get rid of them. And I bet our R squared would jump up. But we are not going to cheat in that way. Again, if we want to know, hey, what can a predictor measurement object tell us? We're going to run properties on it. And here are all the things that we could learn. So, for example, we could also get a residual plot, as we did when we did statistics, or a residual histogram, as we did when we did statistics. And those are those two big residuals that I just spoke about. So that's predict. Let's do classify now. As I mentioned, classify is used where your output's discrete, and here we're going to use it on mushrooms. And what we're interested in is whether the mushroom is poisonous or edible, and as you can imagine, we want to get this right. So let's bring down the data, and here are all sorts of characteristics of the mushroom, and if you want, you can look at description and all sorts of things that are in the example data and learn what this actually means, but at the end of the day, you can see it either predicts it's edible, but some of them are poisonous. Oh, and here's what all these things mean. So the first thing has to do with the cap shape and the cap surface, and if it's bruised, and odor, which by the way is really important in trying to figure out if your mushroom is poisonous or not. In any event, the syntax for classify is exactly the same as it is for predict. It's just classify, and your data, again, in this form of features, goes to value. So let's run classify, and I'm going to watch carefully because it's going to go fast. All right, and as it happened, our AutoML process decided that logistic regression worked perfectly well here. So maybe we didn't need all this machine learning stuff. We could have just stuck with what we learned in statistics, but we're considering alternatives here, and we didn't have to specify basis functions or anything like that. Now, as it happens, I, for various reasons, would like to use something else other than logistic regression so that we start seeing new things. And so again, just as I could force a gradient boosted trees last time, this time I'm going to force the use of a decision tree. So we'll run that, and we're done. It's a very fast algorithm. All right, now let's grab our first 5 mushrooms and their features. There they are. And again, just as we could take pre, and apply it to our Boston Homes features, the first 5 of them, I am going to apply our classifier function, CL, to those first 5 mushrooms. And we learned that some of them are edible, and one of them is not. So just as we could compute a distribution for the predict with a classifier function, we can compute probabilities. It doesn't produce a distribution, it just produces the probabilities themselves, the PDF, as it were. All right, and we can learn we're pretty darn certain the first one's edible, we're pretty darn certain the second one's edible, we're pretty darn certain the third one's edible, we're pretty darn certain that 4th one is poisonous, and the 5th one. So we have a lot of certainty going on here. Hopefully it's right. So let's now see how our model performs on mushrooms that it's never tasted before. Let's see if anybody dies. All right, there's our mushrooms. We've got 2,438 previously unseen mushrooms. We'll take the first 5 mushrooms. We will now apply our classifier to the first 5 mushrooms in our test set. We learned that's what they are. Again, we can get the properties of the classifier. Here are all the things we can ask about. So actually, one of the things you can do with predict and classify is sort of make use of Bayesian updating. You can give it priors, that is, you're pretty certain there are 70% poisonous mushrooms and 30% edible mushrooms in your batch, and you're going to want to have the classifier function take that into account. So we can see were there any class priors used here, and automatic basically is going to say no, there weren't. We could also see what utility function was determining in whether or not it made, in figuring out how to optimize the decision tree. I'm going to show you this, and I want you to think about this for a moment. So right now, the default is, hey, if you get it right with edible, you get a point, and if you get it right with poisonous, you get a point. Now, what you might want instead is you might want that poisonous to be like 100, so you were darn sure of labeling a mushroom as poisonous, and if you had to forego eating a few tasty mushrooms in order to spare you from eating a poisonous one, then so be it. We'll actually come back to this point when we talk about fairness in machine learning classifications, and you can alter the utility function that's used to train in classify, but I'm not going to do that today because this is just a survey, and trust me, it's going to be long enough. All right, so we can actually get a bunch of measurements on how our classifier performs on the test data. When we do this, we get a classifier measurements object that has stuff in there, and you can see right away, hey, we actually did pretty well. And for almost anything but poisonous mushrooms, you would be shouting for joy if you got 99.7% accuracy. We can again get a list of properties of our classifier measurements object. Here are all the things we can ask about it. By the way, by the end of this course, you're going to know what most of these mean, believe it or not. And so we can also get, I can ask it, what's the false negative rate, and what's the Cohen-Kappa statistic? Not that you know what these are yet, but one day you will. And that's a fantastic Cohen-Kappa statistic. And it's telling us that when we think of poisonous as being the positive class, that our false negative rate, that is saying, oh, it's negative, it's not poisonous, the probability that that's false is only 0.4%. And again, for almost everything else one would do, that would be grounds for celebration. I'm not sure I want to go out eating mushrooms where there's a 0.4% chance that my machine classifier has gotten it wrong. I also want to spend a few minutes on a species of supervised machine learning called active learning, and here our Wolfram language function is active classification. Here's the idea. So far we've had the data, we've had the training data at least, and so we built the machine using the training data. But what if data is expensive to collect? Yes, you can compute it if you have to, but it's expensive. So what you'd probably want to do in that scenario is not keep presenting your machine with easy cases. Instead, you'd want to sort of get a rough idea of what the boundaries of the classification was. What mushrooms were you're not sure, is it poisonous, is it edible? And find those mushrooms and focus on them, because if you can solve the hard cases, the odds are you can solve the easy cases as well. And I actually think this has a lot of application to thinking about law, in which, people don't bring cases in which there's an obvious tort or an obvious breach of contract. You tend to see, at least in the opinions that get written about, much more challenging cases, and that goes up. We sort of get closer to the boundary as we go up the appellate chain. But let's move from discussion of law to discussion of the Mandelbrot set. I don't know whether any of you have seen the Mandelbrot set, but it's this unbelievably complicated object that, remember, it uses complex numbers. Remember, those are things that involve the square root of -1 that has a real part and an imaginary part. You don't really need to know this, but just for a little cultural edification here. So figuring out whether a complex number is a member of the Mandelbrot set takes a little bit of time. And so maybe we could use a machine learning to come up with sort of a shortcut that it would get it right most of the time. And the idea here is that because the Mandelbrot set has extremely complicated boundaries, what we might want to do is to look at points that are close to the boundaries. And if we could solve where that boundary lay, then we wouldn't have to keep taxing the machine with figuring out the easy cases. So let's look at the syntax here. And again, it's very similar to classify and predict, except that instead of data, you have a function. You're saying, hey, draw data from this randomly produced data, and then apply this function to see what the answer is. But maybe you don't do every single thing, every single number that's produced by your random number generator. If it seems to be an easy case, maybe you skip it and you go find a hard case. And I'm going to tell it to stop after it's looked at 500 points, because active classification can be much more time consuming than classification where the data is already pre-built. So let's run this. And it's going to take a few moments, but there we go. It's classifying away. We're seeing a little bit of information on progress. Usually down is good. Up, we went back up. Maybe we started going too close to the boundary where it's hard. We keep going. And I think I may do some time compression here. I think this is probably going to take around 20 seconds, 30 seconds. Okay, we're done. And as it turned out, it decided that gradient boosted trees was the way to go, but it used active classification to try and figure out what data points might make most sense to evaluate. We can use the evaluation history property of the active classification object created by active classification. And we're going to get a little data set here if I hit Shift Return. Okay, these are the data points that it looked like, and this is what it determined. Apparently this point is not in the Mandelbrot set, this point isn't in the Mandelbrot set, but this point is in the Mandelbrot set, etc. Now what I'm going to do is I'm going to plot each of the points that it looked at, that's our history, and I'm going to plot those in the complex plane. Again, don't get stressed out about what the complex plane is. And I'm going to color them according to whether they were or were not in the Mandelbrot set. Green means in the set, red means not in the set. And then what I can do is I can overlay this plot on the real Mandelbrot set. And Wolfram Language has a function that's designed to incredibly fast, it's sort of custom written to compute the Mandelbrot set very quickly. So there we go. And what you can see is, first of all, the classification is doing a great job. And secondly, you know, we're not looking at points over here and over here, and we were looking maybe at a few points here, but most of the points we're looking at are somewhat close to the boundaries where the black is. So you can see that active classification is doing a decent job of focusing on the hard cases, which is what you want to do when it's time consuming to collect data. I want to spend a few minutes at this time on neural networks as a supervised learning algorithm. It's a very complex subject. We're going to spend a lot of time on neural networks. I just want to introduce it here. And I'm going to use the good old Fisher iris data to illustrate it. So let's grab our training data and we'll do our terse dimensions thing. All right, there we go. We've got 105 irises with which to train our neural network. Now, what I'm going to do is I'm going to create the architecture of a neural network. The idea is you start with an architecture that has layers, as they're known, and the layers may likely have parameters in them. Those parameters at the beginning will be wrong, but through the training process, those parameters will adjust themselves so that it magically ends up predicting correctly the results of the data. So here our architecture is of a simple form. It's a chain, just one thing after another after another. The more complicated architecture is called graphs, but we're starting off with a chain. We've got 4 layers here. You don't need to know what these layers are right now. They're layers. We're going to input 4 pieces of data, right like that. And we're going to output, we want our machine to output, hey, is this a setosa, a virginica, or a versicolor iris? So I'm going to create that chain. I am going to initialize it, and then I'm going to ask for information on the net. And basically, full summary graphic is, could you make a nice picture of the network? So we do that, and here's a picture, and you can see we've got 4. Let me blow this up a little bit. Let's blow this up to 150. All right, and you can see we've got 4 pieces of data coming in. It blows up to 10. It stays at 10. It shrinks down to 3, and then it produces 3 forms of output, which has to do with the strength, the probabilities of setosa, versicolor, and virginica-ness. All right, again, don't need to know the details, but I thought you should see an image of a network. All right, so one of the things we can do is we can peer in to the values of the parameters in these layers before training. So I'm going to say go into my net, go to layer 1, that's this one, and get the weights. And then it's going to be all weird. We need to normal it and matrix form it. All right, and what you can see is that it's a 10 by 4 matrix. Why is that? It's because we're going to blow up the data from being 4 values to being 10 values. And a 10 by 4 matrix happens to be real handy in doing that. I'm now going to train the network. Okay? And so the command to do this is net train. Net is the architecture. This is our training data. That training data is in the form of features goes to classification. And I'm adding a 3rd argument all here because I want to get sort of all the information it can on the results of our training. So you're going to watch this, and it's going to produce some stuff. You're kind of not going to know the details of it, but hopefully you're going to see a line that starts heading down. Actually, probably 2 lines that start heading down. And in fact, I'm going to shrink again a little bit because I'm not sure it's going to fit on our screen here. Here we go. All right. So it's training, it's going through rounds of training, and you can see that the loss rate is declining. The error rate has gotten down to like 2%, so that's good. It kind of looks like we've stabilized here, not much else is happening. This is very typical, where basically most of the work is done at the beginning, and we are done. All right, so we trained our network. It took 25 seconds. We went through 52,019 training examples. That is, we kept running that data through until we were satisfied. Let's go magnify ourselves up back up to 100%. And now we can take the trained thing that we produced has a property trained net. That is simply the network that we saw before, but with the parameters fixed. Probably fixed isn't the right word. Probably the right word is optimized. All right, but let's use our trained network, and now we're going to do classifier measurements, just as we did when we had a classification, because this is a classifier. And what are we going to run it on? We're going to run it on the test irises that it never saw before. This is going to produce, do you remember, a classifier measurements object. There it is. Only 45 test irises, but let's see how we did. Let's look at the accuracy property and the confusion matrix plot. And we got 95.5% right, and really we got one versicolor that was actually a versicolor. We thought it was a virginica, and there was one virginica that we actually thought was a versicolor. So our neural net did pretty well, not perfectly, but pretty well. All right, so that's an introduction to neural networks, and this concludes our discussion of supervised learning. But now it's time to look at unsupervised learning. Let's look at unsupervised learning. The idea of unsupervised learning is that we have data, but there's no right answer. And so what can we do with that? Well, it turns out a lot. One thing we could do would be to learn the distribution of the data so that we can produce samples that are similar to, but not identical from the data we have. It's like what your law professor does in class. You have a bunch of cases, and the hypo is a case that is similar to the existing cases. It's realistic, but it's not the same, and you have to figure out how the law applies. So let's try learn distribution on some real data. Actually, this time it's legal data. And I'm going to download 13,000 Supreme Court cases from post-World War II. So let's go get it. All right, we've got the data, and you can see actually that there are 13,451 cases, and we have 130 columns worth of information on each case. This, by the way, is the Washington University in St. Louis database adapted for Wolfram Language by me. So what I want to do is to just look at some of the data. I don't want all 130 columns. Here are the things I want. I want to know when it was decided, what type of decision it was, who the petitioner was, the respondent, the type of jurisdiction, the reason for granting cert, the issue area, and the decision directions. And I'll terse dimensions it. And in just a moment, there we go. We've got a bunch of cases. So we've got a case involving decision type 1, which we could look up, which is an oil company against an inventor. The case involves economic activity, and evidently it came out in a liberal direction. Whereas here we have a state case. It's a person convicted of a crime, no reason given, and it came out in a criminal direction. So anyway, now what I want to do is to tell it to learn the distribution of these cases. I do have to hint it here, or it gets a little mixed up. So I'm going to tell it that the first thing is a date, and everything else is what's called nominal data. That is, it's categorical data. All right, so let's run it. And it's trying to figure out how to fit a distribution to this data. Seems to be making good progress. By the way, this stop button and all these learning things lets you stop it prematurely, and you still get an answer. It may not be as good an answer as you would if you let it run, but you do get something. All right, so now we can actually generate imaginary Supreme Court cases. Let's generate 10 imaginary cases. All right, here we have one. A journalist versus a distributor. No reason given for the appeal. It's a First Amendment case, and it came out in a liberal direction. And isn't that cool? It knows that journalism might be connected with the First Amendment. Or let's see, here we have a case of someone involuntarily committed against a mother, and the case involves attorneys, and it came out in a conservative direction. So, anyway, that's the idea of learned distribution. There's actually a lot you can do once you have the distribution, like do things like rarer probability, and look for outliers, all sorts of fun things. Let's look at another form of unsupervised learning called dimension reduction. So often you have very fat data. You've got lots and lots of columns. And it's very difficult to visualize that kind of data. And sometimes machine algorithms will encounter difficulty, or it'll take a lot longer if you have hundreds and hundreds of columns. Oftentimes the information in those columns is redundant, like the value of one column correlates very closely with the value of another column. You don't really need both. So you might want to reduce the dimensionality of the data, reduce the number of columns in effect. So I'm going to try that here, and I'm going to grab some data on baseball. This is where it is on my hard drive. I'll put it up on the Wolfram site, and you can try to grab it from there if you want to replicate this. But we're going to import that data. It's a CSV file, a comma-separated value file. I'm going to import it as a data set, and the first line of the CSV file, as is very common, are the headers. So here we go. We're done, and here's the data. You can see that we've got players from 1871 that no one's ever heard of, who played for teams that no one's ever heard of. But in any event, and you can also see that there's actually more data here, more columns. There are 22 columns. We're only seeing 10 of them. We could look at, let's see what the last piece of data it has is. It has the data from the 2018 season. And isn't this Ben Zobrist, I believe, who played for the Cubs? And you can see his statistics here and more statistics here. All right, so that's the data. And what we want to do is to get rid of, you weren't supposed to see that. That's junk. Get rid of that. What we want to do is to get rid of some of the columns that I'm not going to use or that are incomplete when we go back to the 19th century. So you don't even have to worry about what these are. I'm getting rid of them. And then I'm going to use a function called delete missing, which says that if anything is missing at level 2, delete it at level 1. So there we go. And now I've got a cleaner data set, which only has 17 columns rather than the 20-something we had before. And as a result of getting rid of some things, we have 105,861 baseball players, which is really more than enough as far as I'm concerned. What I now want to do is to create a dimension reducer function, which when we apply it to data, will produce data that has many fewer columns than we started with. So here what I'm going to do is I'm going to drop out information that I don't need, like the player ID and the team ID. That really doesn't fit with the rest of the statistics. And I'm going to boil it down to 2 columns. So we're going to take our batting data and we're going to boil all those, well, it's really 15 columns because I'm taking out 2, down to 2 columns. All right, so here we go. And there we are. All right, we have a dimension reducer function. It's sort of like a classifier function or a predictor function or an active classification function. Now we have a dimension reducer function. And you can see that it takes 15 numbers, produces 2, was trained on 105,000 examples, and it's using some linear method to do this. There are a lot of methods of doing dimension reduction. I'm not going to explore those at the moment. Okay, so let's get some data on the 2017 Astros, who you may remember won the World Series, but then it turned out they were possibly cheating. But we won't get into that right now. What I want to do is I'll use the select function. I want the year to be 2017. I want the team to be Houston. And I want people who actually played in a fair number of games. So let's do that select on the batting, and we will get the Astros 17. There they are. You can see, you sort of have to know how to read this, but this is Carlos Correa and Evan Gattis and Marwin Gonzalez and Jose Altuve and all that stuff. So again, you don't really need to know this, but there you are. All right, now what I'm going to do is I'm going to drop the player ID and team ID, because that wasn't included in my dimension reducer function. And then I'm going to apply that dimension reducer function, drf. Maybe I should replace that with just drf. And it's going to produce a two-dimensional version of the Astros players. And there they are. There are the coordinates of the Astros players. It's hard to know what all that means, but let's see if we can run some code that helps us. We're just going to get their names in a reasonable form, and then I am going to make a labeled plot of the Astros. And so we can see we've got Jose Altuve up here, and we've got Alex Bregman, who hit a lot of home runs that year. And then on the other hand, we have players who might not have been as effective. We've got Cameron Maybin, and I'm not actually sure who that one is. We've got Derek Fisher, who was a good runner, but didn't play that much, etc. Anyway, so the idea is we have grouped players who should be similar in characteristics, like Altuve and Springer, together, and that's what dimension reduction can do. Cluster classify. So we've already seen how you can classify data using supervised machine learning, in which we already know the cluster, i.e. species, to which the data iris belongs. But turns out you can cluster data even when there is no supervision. The idea is to put data that lies near each other together into the same cluster. And actually, this is sometimes called semi-supervised learning, because you're going to use these data points to help classify future data points. But in any event, let's generate our data. We're going to use something called a mixture distribution, which is sort of a distribution of distributions. The idea is a third of the time we're going to go from this multinormal distribution, a third of the time from this one, and a third of the time from this one. We'll pick 100 random variables from that. We'll assign that to RV, we'll plot it, and I've seeded our random generator so that these results are replicable. And here's our data, and we want to cluster it. So the command for clustering is, it's very much like the other machine learning things. It's just cluster classify and then your data, which in this case is RV. And we'll call the output CF. And so there we go. Now we have a classifier function. We've seen classifier functions before. And so we did classification not through knowing what cluster something was in or what the output was, but simply by figuring out whether it was similar to other things and dissimilar from others. All right, we're going to make a nice picture of this. We're going to associate with each point its cluster. So we're going to take CF, the cluster function, and apply it to our random variables, and then we'll thread that with the random variables themselves. We will terse and dimensions it. And now for each of the 100 points, we have the point and their cluster, the point and their cluster, the point and their cluster, etc. And so now we can plot the points. I don't think you need to worry about this code. Just it's going to be colored red, green, and blue depending on what cluster it is in. And you can see, even though I didn't tell it, find 3 clusters, that's what it did. And I have to say that seems like a very sensible clustering to me. And so, in fact, one thing you can do is now that you have a clustering function, we can take this plot here, the clustered training plot, and we can overlay on it what color we should give to any new point. I'm going to use manipulate. There's our show that combines the this plot with a new plot, and we're going to have a point on that plot. This is the first time we've seen a locator object. I think it's just easier to show it to you. Okay, so here it is, and I can move this around. I'm moving this with my mouse, and as I move it, you'll see it changes color. Right, let's see, right, red, blue, red, blue, and then if I come over here, it turns green. So you're seeing the boundaries of the cluster definition. And in fact, you could do that even better. I'm going to generate 5,000 points. I'm going to apply the cluster function to that, cluster classifier to that, and we'll visualize the result. And now you can see that from just data, not from supervision, from data, we have some idea as to what cluster future points belong to. Now for a new and exciting area of unsupervised learning, which is, I'm going to call adversarial learning. I'm not sure there's a canonical term for it, but that's what I'll call it. And the idea is that either the machine learning systems battle each other, or you kind of figure out how to defeat them. So let's talk about adversarial attacks. And there's a great example. It doesn't quite come from machine learning, but I kind of like it. So supposing you have a company like US News and World Report that rates the quality of a school. And it turns out that good schools have lots of money, and schools with lots of money tend to have big libraries. So it's hard for US News to go in and actually rate the quality of a library collection. So instead, they might use a proxy for quality, which might be the number of volumes possessed by the library. And that actually works pretty well until the schools realize, wait a second, if we just increase the number of volumes in our library, wouldn't make a darn bit of difference with respect to the quality of education. They could just be, you know, Bernstein Bear books or something. Still, our ratings with US News could go up. Or maybe we could buy an electronic collection that had lots of volumes in them. So we could exploit a weakness in the machine learning system into thinking that our school had improved its quality when in fact nothing had really changed. All right, but let's be a little more scientific in what we mean by an adversarial attack. And the idea is to exploit its weaknesses. It's generally done with neural networks, although you can certainly have an adversarial attack on other forms of machine learning. By the way, this work is pilfered significantly from a post on the community.wolfram.com website by, actually, I think he's a teenager, Nico Adomo, who did some really fine work on this. All right, so let's actually look at a list of images, and they might be too small to see here in this video. Let's blow things up a little bit, just for the moment. All right, so you can see, I think you can see that's an ostrich, in my opinion. That's a boat, maybe a catamaran. I think that's a guitar, and that's a gun or a six-shooter or a revolver or something like that. All right, so that's what we're working with. That's what a human being, me, has identified them as. But now let's see if a machine can identify them. And we're going to load in a fairly early version of image identification, of machine vision. This is called the Inception neural network. This is by no means state-of-the-art. Maybe 10 years ago it was state-of-the-art or something, but no longer. But it'll do our job. So let's load that up. There we go. We've sucked it in from the Wolfram Neural Network repository. It's a net chain object. Remember I talked about net chains before? And now I'm going to run that neural network on the images. And look, it got it all right. That's an ostrich, that's a catamaran, that's an acoustic guitar, correct, and that's a revolver. So that's great. But now let's try something else. Here's a function, and this is the one written by Nico Adomo,
that takes an image, it takes the network that you're going to be using for identification, and it tells you how much to perturb it. And it's going to figure out some basically perturbed image that it thinks is likely to fool the classifier. So let's put that into the kernel. Now, let's map our trickery, 10% trickery, over our images. And we'll get a list of perturbed images. Just wait. All right. And I think any human, what's that? It's an ostrich. Still a catamaran. Still a guitar. Still a revolver. Let's see what our machine thinks it is. Same machine, just running on the perturbed images. It thinks that's a limpkin, which, by the way, is a kind of wading bird. A trimaran, so it's confused on that. It's turned this somehow into a hatchet, and it still understands that this is a revolver. So, what you've seen, though, is that you could try with things that wouldn't fool a person, but for the machine, it's like an optical illusion. They just can't handle it. And so, if you can get a hold of the machine or start running examples on it, you can often figure out how to trick it. Generative Adversarial Networks, or GANs. Okay, so here's the idea. I showed you how you can generate realistic but not real Supreme Court cases, and I did so using learned distribution. But there are other methods, and I'm betting many of you have actually seen this method in action if you've looked at websites like thispersondoesnotexist.com, which depicts incredibly realistic looking people that are in fact complete fabrications. They don't exist. So how does this come about? It's actually quite simple and quite brilliant. You take data tends to be in a low dimensional space, like maybe 10 numbers, 5 numbers, something like that, and you run it through a neural network called the generator that outputs data in a high dimensional space, and certainly neural networks can do that. So perhaps that high dimensional space is an array that could represent an image. It could have a red, green, and blue value, red, blue, and green value for all of its pixels. And at the start, the parameters of the generator are basically random, so you get, nonsense images out of it. You then feed the output from the generator into a completely different neural network, the discriminator. And you also feed the discriminator with things that are real, like real faces or real cases or whatever you're trying to produce similar items of. And the job of the discriminator is to figure out, hey, is this thing that I'm seeing fake, meaning generated, or is it real? And the generator and the discriminator then co-evolve. The generator is rewarded when it fakes out the discriminator, and the discriminator is rewarded when it sees through the generator's tricks. And at the end of this process, which can take a very long time, we get both really good generators and really good discriminators. At this point, in general, after all that work, we throw out the discriminator, and we're left with a generator. But what can the generator do? It takes in data in low dimensions, and it produces output that the good neural network, and probably good human, cannot tell apart from the real thing. So, unfortunately, training a GAN on a machine that does not have a GPU like this is really tough. And so I'm just sort of going to show you the beginnings of this. I've taken this example from the Wolfram Language documentation for the key piece of code, which is called the key function, which is called netGAN operator. And so I'm going to go through this rather quickly because my main point is to just sort of explain to you what a generative adversarial network is. They're basically a way of synthesizing realistic examples from the battle of two neural networks. So we can get the famous MNIST dataset. MNIST is sort of one of these things like the Fisher Iris dataset. It's a bunch of numbers that people used, I think, to write zip codes on addresses, and you take each, let's just see it. You just take each number here. And so we have 60,000 of these things, and it's going to say, okay, here's the image, And I, being a smart human, I know that's a 6, that's a 6, that's a 0, that's a 2, that's a 6, that's a 4, that's a 4, that's a 6, that's a 9, that's a 1. And you want a machine that can basically read bad handwriting. So what we're going to do is we're going to create the architecture of the discriminator. You do not need to understand this code. I'm going to take the architecture that generates the generator. I'm going to create a function that goes from the low dimensional space to the high dimensional space. I'm going to create some auxiliary stuff that need not concern you. I'm going to create a function that generates digits. So here we have, what is this? A 6 by 6 array of things that we're starting out. Remember I told you in the beginning it produces gibberish. And so those don't look like digits, those just look like noise. But the hope is that by training our system, and here's some of the code that we're going to use to train it, it's basically just net train, and this is a lot of visualization code that's added to it. And at the end of the day, you get something like the following. So now I'm actually in the Wolfram help documentation, and I want to go down to the discussion of this digit synthesis. And here we go. So they actually ran the training. This is the same code I have, except that they ran it on a GPU. And you can see when we start off, early on, our generator is producing gibberish. But as we evolve, we're starting to generate things that sort of look like smudged letters, and training's continuing, and now some of these are looking like letters. And as we keep going, at the end, basically we get things that look a lot like letters. And so our generative adversarial network has basically done what most 3-year-olds can do, which is, I think they can do, which is to write their numbers. So that's the concept of a GAN. Let's talk about one other form of learning, which is reinforcement learning. So reinforcement learning is probably the most complicated of the things that I'm talking about. And for better or worse, Wolfram Language does not currently have great support for reinforcement learning, so there's not much code I can show you. But where it's used is where you have a complex task over time, where it's not clear that there's a right answer. There are wrong answers, like if you're trying to train a self-driving car, crashing would be bad. If you're trying to teach a machine to play chess, getting checkmated would be bad. But often that reward is not immediately apparent. Like, you move the pawn forwards and it turns out 5 moves later that was a big mistake. So the idea of reinforcement learning is you have an agent, they make choices, those choices affect their environment, which in turn affects the rewards that they ultimately get. I think the best way to learn about it is actually to watch some YouTube videos. I've picked out 3 here that I kind of like. This first one, and if you press this button here, this is a button, you'll actually get to it. It'll open in a browser. It's about how to play hide and seek. And it turns out the little AIs are incredibly smart at playing hide and seek after they play for a while. This one, I believe, is on simulating soccer. I think it's maybe FIFA. And basically, in soccer, you've got to think about short-run gains and long-run strategies. And so this YouTube video shows how reinforcement learning can do that. And then this is a video on the beginning, the math of this all. There are lots of methods of doing reinforcement learning. One of the most standard is called Q learning. It's difficult. I have to say, this is not an easy area. But if you want to start learning about it, this is where I might send you. So that brings us to the end of this long introductory video. I can't emphasize enough what a big and exploding world machine learning is. 10 years ago, a lot of this stuff didn't exist, and it has just grown exponentially. What I've tried to do in this essay and video is to show you the main branches of machine learning. In future videos, we're going to sort of double back on a lot of what I've covered here and look at, random forests and nearest neighbors and unsupervised clustering, all that stuff in greater detail. For now, though, I think this will give you a good background on what machine learning is all about.